Okay, so welcome everyone to a new session of our category seminar. Our speaker today is Sarazola from Cornell University, who will be speaking to us about the stable homotopy hypothesis. If anyone at any point wishes to ask a question, please unmute yourself or ask the question in the chat. Yeah, please take it away, Maru. Thank you.
Yeah, thanks, Juan, and thanks so much for the invitation to speak here today. So I'm going to be telling you about a paper that I did with my co-authors, Lynn Moser, Victorio Sornova, Simona Pauli, and Paula Verdugo, which is called the Stable Homotopy Hypothesis. So the way that the talk is going to go is we're going to start by talking about the classical homotopy hypothesis, which you might have heard about before, but if you haven't, that's totally fine. So I'm quickly going to tell you what that one's about, and then we're going to see a specific model that solves, let's say, the homotopy hypothesis. And then we're going to talk about the stable version, which is what our paper is about. So I'm going to tell you what the stable homotopy hypothesis is and what should go in the categorical side, and then I'm going to give you a sketch of the proof. So like I said, the first part of this talk is not going to contain anything new, really. It's just mostly going to be a recap of the classical homotopy hypothesis. So here we go. All right. What is the homotopy hypothesis? Well, it's the statement that topological spaces are the same as infinity groupoids. Now, for the purposes of this talk, I really only care about homotopy theory. So when I say the same, what I really mean is that their homotopy categories are equivalent categories, where in spaces, we are taking the weak homotopy equivalences as the weak equivalences, and then we are taking higher categorical equivalences in the groupoid side. There's even a more refined version of this statement that specializes the equivalence to level n. And this version says that n types are the same as n groupoids. So what are these characters that we see here involved in the statement? So we have a topological side on the right in the previous slide that deals with n types. So these are going to be the topological spaces whose homotopy groups are concentrated in 0, n. So any homotopy group higher than n is going to vanish. And like we said, when we take the homotopy category, we are inverting the weak equivalences, meaning the continuous maps between spaces that give us isomorphisms on every single homotopy group. So that is it for the topological side. And then on the categorical side, we have these things called n groupoids. But there's a problem here, because although the topological side, there's consensus on exactly what all of these words mean, on the categorical side, we find that n groupoids are going to be different things depending on whom you ask. So what do I mean by that? I mean that there exist many different models of n groupoids in the literature. But of course, we're not just going to go and call anything an n groupoid. They need to have a common theme. And it's generally agreed that any notion of n groupoid should consist of some variant of an n category with invertible cells above level 0. So the picture that you want to have in mind, and this is going to be a very hand-wavy, not a definition at all, but you want to think of a structure that has 0 cells, which we think of as points or as objects. It has 1 cells between 0 cells, which you can think of as morphisms. And then if you have 2 1 cells, you're allowed to have a 2 cell between them. And if you have another 2 cell, you're allowed to have a 3 cell between those, and so on and so forth until level n. And then the groupoid part says that all these arrows that are drawn here should be invertible. Okay, so that's kind of the idea of what an n-groupoid should be, but finding a concrete, usable definition of n-groupoid that satisfies the homotopy hypothesis is not a trivial thing. And in fact, the pursuit of coming up with these models has greatly informed the foundations of higher category theory.
I'm sorry, Maru, we have a question in the chat.
Yeah,
So
absolutely.
Jose Antonio is asking if n types is K homotopy for K higher K ignored or required to vanish.
What, sorry?
So yeah, I think Jose Antonio can unmute himself and maybe ask the question.
Hello, the question is only if higher homotopy is required to vanish or is just ignored? Like,
oh, no, it's required to be 0.
Okay, and no one considers the other case in which you consider things that are different because of higher homotopy as equivalent, even if they are different? Like consider equivalence classes of those?
Could you say that again? I'm not sure that I understand.
I am saying if you have two spaces in which their homotopy up to level n are the same but different later, and if you consider the option of considering those as equivalent and working with these kind of objects, is it something that it has been explored, or is it interesting for you?
Okay, I see what you mean. Honestly, I have no idea. I suppose it could be interested in if one is studying something like Plasnikov towers or something like that, but honestly, I don't really know anything about that. But I don't think I've ever seen that as a class of weak equivalences for the purposes of like studying model structures or something like that. Yeah, but in this case, no, we are definitely requiring anything above n to be 0.
Thank you. Thank you.
Okay, so we were saying there are a bunch of different models of n-groupoids out there. But of course, since we said all that we really care about is things up to homotopy, and since any model of an n-groupoid should satisfy the homotopy hypotheses, that means its homotopy category should be the homotopy category of spaces. And so in particular, any models are going to have equivalent homotopy categories. And so for homotopy purposes, that's not really an issue. Okay, so in a little bit, I'm going to show you a specific model. So you will get to see more of a definition of what we think of as an n-groupoid. But for now, let's use this vague idea that I've given you to get some intuition about why the homotopy hypothesis is something that we expect to be true. So remember, the statement was topological spaces are the same as infinity groupoids. So why is this something that anybody would expect? Well, the key is to look at spaces from a very particular perspective. Let's say that we have a topological space here. What we want to do now is we want to think of the points of the space as objects. And then between 2 points, we can have a path. So we're going to think of this path as a one cell. And now if we have another path, we may have a homotopy that deforms one path into the other. And we're going to think of these homotopies as 2 cells. And if we have another homotopy, then you can have a homotopy between the homotopies themselves, and these are going to be the 3 cells. And at this point, you should have seen that I'm drawing exactly the same picture that I was drawing when I told you what an n-groupoid is. So this is where we see the connection, when we look at spaces from this perspective. And of course, we said all of these paths, all of these arrows need to be invertible. And in spaces, that's indeed the case, right? Because if you have a path, you can run the path backwards in time and up to homotopy that will give you an inverse of the path. And you can similarly run the homotopies back in time and get an inverse homotopy. Okay, so the lower cases of the homotopy hypotheses are things that are pretty easy to see, or at least kind of familiar to us. So let's look at the cases n equals 0 and n equals 1. For n equals 0, in the categorical side, we have 0 groupoids. So since n is 0, we only have 0 cells and nothing else, which means this is a set of 0 cells. On the topological side, we have 0 types. So these are going to be spaces that are allowed to have a bunch of connected components because pi 0 doesn't have to vanish, but all the other homotopy groups have to vanish. So each of those connected components is going to be contractible. This means up to homotopy, this space is the same of the set where we have 1 point for each connected component because we can just contract each of those. So we can see that for n equals 0, both sides of the homotopy hypotheses are just sets. N equals 1 is not as trivial, but still quite familiar. And it boils down to the correspondence between 1 types and groupoids given by the fundamental groupoid functor on one direction and its inverse given by geometric realization. So far, there's nothing really new going on here. But when we reach n equals 2, there's a break-in point here, and we find that for n greater than 2, strict n groupoids are not sufficient to model n types anymore. And what I mean is that instead of having a higher category, having unitality and associativity work up to equality on the nose, we're going to need to relax this structure and get a weak higher category if we want to encode all the n types. Now, in order to build a model of a weak n category, we need to find a machinery that encodes in an efficient way the sets of all cells of dimensions 0 all the way up to n. Now, we also need to encode the behavior of the compositions. And finally, we also want to encode the data of higher categorical equivalences, because at the end of the day, we're going to want to consider the homotopy category. So we need to know what we're inverting. And this is where the different models come in. But a natural way to do this is to use multisimplicial sets, because they give us a very natural way to encode the composites if we use the Siegel maps. So now let me show you a glimpse of the model that our team chose to use for our paper, which is the Thompson-Money model. And this is not going to be crucial for the purposes of the talk. I'm not going to be very detailed. But I just do want to give you an idea of what these creatures look like. So let's start by considering a simplicial object in a category C. Remember that delta is the category of finite sets and order preserving maps, order preserving functions. So if we take a functor from delta ob to C, that's what we call a simplicial object in C. And for any of those objects, we can define the Siegel maps. So for each k greater or equal than 2, we form this diagram that you see right here. And then if you look at the lower 2 levels, the ones with x1 and x0, and you take the pullback of all that picture, you get this thing here. And so we have an induced map from xk, which is the apex here, to the pullback just by the universal property. And that unique map is what's called the Kayth-Siegel map. So in case you haven't seen these before, let me try to unravel quickly what this is doing for k equals 2, just to make it really clear why these are related to composites. So for k equals 2, our Siegel map is going to go from the set of, let's say we're working with simplicial sets to make things a bit simpler. We're going to go from the set of two simplices to the pullback of x1 and x1 along x0. So what are these things? Well, the two simplices we think of as triangles with directed edges. And if you really write down who these eta 1 and eta 2 are and who the face maps are, you will find that what the Siegel map is doing in this case is it's picking out these two edges of our triangle. So what the Siegel map is doing is it picks out the composable maps. Right? So this is why I'm saying it's natural to use these Siegel maps to encode data about composites. So how are we going to do that? Well, our model, like we said, is called the Thomson-Money model. So these are Thomson-Money N categories. And these are defined by induction on N. So the definition is actually quite complicated, but I do want to give you the idea. So for the first few levels, we say the Thomson-Money 0 categories are just sets. The Thomson-Money 1 categories are categories. And then for n greater than 1, remember that our goal when defining a Thomson-Money N category is going to be to find a way to record cells in dimensions 0 up to n, and to find a way to encode their composites. So how are we going to do that? Well, we're going to say a Thomson-Money N category is a functor from n-1 copies of delta op to cat. Or equivalently, if we see cat as a simplicial set embedded via the nerve, this is going to be a functor from n copies of delta op to set, such that they have equivalent Siegel maps in all the simplicial directions, right? Because now we have a multi-simplicial set, so we have n many delta op directions, and we have a lot of Siegel maps that we could be taking. We're going to ask that all of those are equivalencies. Then we're going to use x0 to record the set of 0 cells, and similarly x1110 to record the set of R cells. And then for the highest two cells, for the n-1 and the n cells, we're going to know that once you fix all of these n-1 directions, you are left with a category. So we're going to use the objects of that category to encode the n-1 cells and the morphisms of that category to encode the n cells. We're working with small categories all the way. All right, so that is how these Thomson-Money N categories encode all the data of the cells. And for composites, we're going to use the Siegel maps and our condition that these have to be equivalences, because now if we have two composable maps in the pullback like this, then how do we compose these? Well, since this map is an equivalence, then up to homotopy, we have an inverse. So we have a way of going from the pullback to x2, meaning we have a way of filling this composite to the data of a triangle. And then we use this D1 face map, which picks out the bottom segment. So in other words, we start with composable maps, and we have a way of picking out a composite for them. Okay. And then, of course, we also need to say what the equivalences between these things are. And these are also defined inductively. But basically, zero equivalences are bijections. You'll remember that Thompson-Money zero categories are sets, so this makes sense. Thompson-Money one categories were categories, so their equivalences are going to be the usual equivalences of categories. And then for the higher levels, an N equivalence is going to be a higher dimensional version of fully faithful and essentially surjective. So however you can extrapolate that using higher Holmes is what you get for the higher equivalences. All right. Now, once we have Thompson-Money and categories, which is what we've seen so far, we can define Thompson-Money and groupoids, which is actually what's going to be the player for the homotopy hypothesis. And we said Thompson-Money zero groupoids are all sets. Thompson-Money one groupoids inside of categories are just the usual groupoids, so the categories with all morphisms invertible. And for the higher ones, the intuition is that we want to be able to say that whenever we fix a simplicial direction, we get a lower dimensional Thompson-Money and groupoid. So this is where the induction kicks in. Okay, so of course, like we said, we're interested in these things because they do solve the homotopy hypotheses. In fact, Thompson-Money proved that if you consider the geometric realization functor from Thompson-Money and groupoids to topological spaces, then you find that those spaces in the codomain are actually N types, and that furthermore, this induces an equivalence between their homotopy categories. All right, so perhaps this is a good moment to pause for questions before we move on to the second part of the talk.
Yeah, Paul, go ahead.
So the Thompson-Money means the presentation in terms of these Siegel maps. Is that what the name means?
The Thompson-Money what, sorry, Paul?
So when you describe something as a Thompson-Money model, I mean the bit that we're naming that, is that the what you've got as being the D1 from X2 to X1 on that slide?
Yes, that's the most important part. There's another technical details that go into making the induction run properly, but that is the piece of information that's most important. Yeah.
Right. Okay. Right. Thank you. By the way, I went to Emily Reel's talk yesterday on a similar subject and didn't understand any of it, and your presentation is much clearer.
Okay. Right. Okay. So the second part of the talk is going to deal with the stable version of the homotopy hypothesis, and this is where the new results are going to come in. So if you zoned in for the first part, this is a good time to join us again. So we should start by saying, what do I mean when I say stable homotopy hypotheses? Well, what I mean is that instead of studying topological spaces, we are going to study spectra. So what are spectra, in case you've never seen them before? A spectrum is a sequence of pointed spaces together with structure maps that relate the suspension of a space with the following space in the sequence. And this is literally all that they are. It's a sequence of spaces with these suspension maps, and that's the end of it. So you might wonder, the definition is pretty unremarkable. Like if you've never seen these things before, you might be wondering, why do we care about these? So that is a fair question, but in fact, it turns out that for many reasons, spectra are key objects of study in algebraic topology. So let me highlight my favorite reasons, and I'm sure that If you ask another algebraic topology, they're going to have their own set of reasons why spectra are so important. But for me, what's really cool about these is, first of all, they give a sense to a notion of negative homotopy groups. So as you know, in spaces, we only have positive or zero homotopy groups, but spectra, the way that these are defined, allow for negative ones as well. They provide a natural setting for the study of stable homotopy groups. So perhaps if you've been to some topology talks, you might have heard the buzzwords stable homotopy groups of spheres, which is something that topologists really care about nowadays. Well, this is the right setting to study those things. They contain all infinite loop spaces. And so through these, spectra characterize all cohomology theories. And finally, they can be interpreted as an abelianization of spaces by May's recognition theorem. So a poor man's analogy would be that spaces are to groups as spectra are to abelian groups, or something like that. Okay, so if we want to have homotopy hypotheses for spectra, we need to have an analogous notion of n types for spectra. And in fact, there exists such a thing pretty much verbatim. So there's a way to define homotopy groups of spectra, which I'm not really going to go into, but maybe since these are clearly topological creatures, you'll believe me that such a thing exists. And we say that a stable n-type is a spectrum such that all its homotopy groups vanish outside of 0n. In particular, all the negative ones have to vanish as well. So now that we have homotopy groups in hand, we have a notion of weak equivalence. So a map of spectra is called a stable weak equivalence if it induces isomorphisms in all their homotopy groups. So just like the classical topological case. And in case you're wondering, these are in fact the weak equivalences of a model structure. So Bousfield and Friedlander proved that the category of spectra admits a model structure with the stable weak equivalences as its class of weak equivalences. All right, very well. So now our stable homotopy hypothesis is going to say, the classical case, to recap the classical case, we had that n types with weak equivalences are the same as n groupoids with higher categorical equivalences. So in comparison, the stable version is going to say that stable n types with stable weak equivalences, as we've seen in the previous slide, are the same as what? So now we need to put in some effort to figure out what needs to be in the categorical side. All right, so how can we figure that out? Well, what we're going to do is we're going to draw intuition from infinite loop spaces to try to figure out what kind of properties we should be looking for in a categorical model for these things. And in case you're wondering, well, that sounds like cheating. I mean, infinite loop spaces are really nice. Why would these be representative at all of the entire category of spectra? It might comfort you to know that these are indeed the fibrant objects in the model category with the weak equivalences that we are considering. So it does make sense to draw intuition from these. All right, so now let's look at loop spaces. And we quickly see that we have a product. So we can multiply loops by concatenating. You run one loop after the other and you get a loop. And this multiplication turns out to be associative, unital, and commutative up to higher homotopies. So these properties are not going to be true on the nose, but they will be true up to homotopy. So what this tells us is that we expect the corresponding n groupoids on the categorical side to have a symmetric monoidal structure that encodes this commutative product that loop spaces exhibit. But loop spaces are even more special because, like we said at some point, if you run a loop and then you run it backwards, you get an inverse up to homotopy. So since loops have inverses up to homotopy, but now remember in our loop space, the loops are the elements. They're not the morphisms. So we're saying that in a way, the elements have to have inverses. So the objects in our N groupoids are expected to be invertible in some sense. So when we put all this intuition together, we arrived at the fact that the categorical side in the stable homotopy hypothesis is going to be given by group-like symmetric monoidal N groupoids, which are called Picard N categories. Okay, so now our stable homotopy hypothesis is going to try to prove the fact that stable N types are the same as Picard N categories. All right, so just like what we did for the classical case, let me show you a little bit of evidence for why this statement is expected to hold by looking at the lower cases. So if we look at N equals 0, stable 0 types are what we call Eilenberg-MacLane spectra. And on the categorical side, we have Picard 0 categories. So these are 0 groupoids, meaning they only have 0 cells and nothing else, except that now we need to have a symmetric monoidal product that additionally makes every object invertible. So we have a set of 0 cells, we can multiply them. This is symmetric, so we have a commutative multiplication, and each object has an inverse. So in other words, we have an abelian group. And it's known to topologists that abelian groups are in one-to-one correspondence with Eilenberg-MacLane spectra. All right, so what I'm going to do now is I'm going to introduce a different perspective. So a different way to encode the data that I just mentioned, which might seem a little bit artificial, but it's really going to be key for the rest of the talk. So let's say that we have an abelian group. What is an abelian group? Well, we have objects, let's say G1, G2, etc. We have a product, G1 times G2. And since it's abelian, we know that G1 times G2 equals G2 times G1. Okay, everything is obvious here. But what I want to show you is a way to categorify this data. We can encode this exact same data by shifting one dimension up and describing an abelian group as a one groupoid with one object. So I want to define a groupoid. So this in particular is a category. So I should tell you what the objects are, and it's going to have just one object. I should tell you what the morphisms are. And now if we have our only object here, the morphisms look like loops, right? Because they start and they end at our only object. And we're going to have one such morphism for each group element. And then the composition in our category is going to be given by the product. Okay, so this is a very simple way to see how we can encode the group structure, which is kind of at level 0, because we're only talking about 0 cells, by shifting one dimension up and now considering a groupoid with one object, and we use its morphisms in level 1 to encode all the group structure. What's missing is the symmetry. So in this process of categorification, we see all of the group structure for free, but we don't see the abelianness. So that is why here we're saying plus symmetry, because that needs to be encoded separately. So additionally, we need to impose the symmetry condition, which is now imposing that composition is commutative in the category. Okay, So this fact is going to come up again. So the important thing to remember is that by shifting one dimension up, we can describe the abelian groupoid as a one groupoid, the abelian group, as a one groupoid with one object if we are able to encode the symmetry separately. All right, so that was it for the 0 case. For the 1 case, it's already not trivial. It was proven by Patel that stable 1 types correspond to Picard categories, where these are defined as groupoids with a symmetric monoidal structure and invertible objects. Or alternatively, if you allow me to do the same shift in dimension, these can be seen as groupoidal bicategories. So here we are at dimension 2, with one object plus some added symmetry. And finally, the case n equals 2 is due to Gursky, Johnson, and Osorno, and they say that stable 2 types correspond to Picard bicategories. And this is as far as the literature went, 0, 1, and 2. So the goal for our project was to generalize this and give a definition of Picard weekend category that satisfies the homotopy hypothesis for all n. Because just like what we said, okay, an n groupoid needs to have cells and invertible cells and blah, blah, blah. But we said, okay, that's not a concrete definition. Then a concrete definition is, for example, given by the Thomson-Money model, which is a big thing with specific structure and specific ways to encode all that data. The same happens for Picard n categories. We have our motivation of what a Picard n category should be, but part of solving the stable homotopy hypothesis, and one might argue the hardest part, is to give a concrete definition of what these Picard n categories should be. So let me try to show you how we do that. And you might be wondering, okay, why can't you just copy the definition you've been using so far, and instead of using the number 0, 1, or 2, just put an n and use what you get? So if you remember, Picard 0 categories were abelian groups, or as nobody likes to call them, group-like groupoidal symmetric monoidal 0 categories. And then if we change that 0 by a 1, we get Picard 1 categories. And if we change that by a 2, we get Picard 2 categories. So why can't we just say a Picard n category is a group-like groupoidal symmetric monoidal n category? Well, if you've ever worked with higher categories before, you might know that symmetric monoidal bicategories are already incredibly hard. So I'm talking about a gazillion diagrams, an incredible amount of bookkeeping that you need to do. So it's doable, but it's really, really hard. And it's in fact so hard that there's not even a definition currently for symmetric monoidal n categories for n higher than 4. So really just putting an n into the sentence is not going to solve any of our problems. Instead, what we're going to do is use this change of perspective that I was telling you about, where we shift one dimension up to encode the monoidal structure. So a Picard n category, what we're striving for is for a notion of group-like symmetric monoidal n groupoid. And like we saw in some specific cases, we can encode the monoidal structure on the groupoid by shifting one dimension up. So a monoidal n groupoid carries the same information as an n plus 1 groupoid with one object. And now the good thing about doing this is that on the right side of this equality, there's no monoidal product. So there's no new definition that needs to be made here. All right, so now we have a monoidal n groupoid. And now the original object, since we did this shift in dimension, what were before our objects are now our 1 cells. And so since we have a groupoid, we already have the group-like condition encoded for free. What we're missing is the symmetric part. So just like the case for abelian groups, the symmetry in the product needs to be encoded by hand. So now to show you how to do that, let me be a bit more precise because I've been saying N groupoid all along, but like we said, there's a lot of different models. So let me shift to the specific model that we want to consider, which is that of Thomson-Money N groupoids. And now the question becomes, how do we encode the fact that the monoidal product has to be symmetric? Well, if you'll remember, a Thomson-Money n+1 groupoid is a functor that looks like this, satisfying a bunch of additional things. And the monoidal product being symmetric is the same as the composition here being commutative. So how do we compose? Well, like we said, we compose using the Siegel condition. That is why we require this to be a weak equivalence, so that we can flip it up to homotopy and go the other way. So in order to introduce the symmetry in this composition, we're going to extend the first copy of delta op to a gamma. So here we have n+1 copies of delta op. We're going to extract the first one. We're going to look at it like that. And then we're going to turn the first delta op into a gamma. So just to remind you what these things are, this was the category of finite sets and order preserving functions. And by gamma, I'm denoting the category of finite pointed sets and base points preserving functions. In particular, and what's going to save us here is that in gamma, we don't need to be order preserving. So we have a lot more freedom for our class of morphisms. All right, so let's go ahead and do that. We separate the first delta op. We turn it into a gamma via an embedding that we have of delta op inside of gamma. And now this D1 that we used for the composition before, now we want to pre-compose it with the embedding. So this is going to be our phi D1, which is the map that collapses everything in the set 2 to the element 1. Okay. So why is this any good? Well, the key here is that in gamma, we're allowed to twist. So we can consider this twist T from 2 to 2 that flips the elements 1 and 2, which we couldn't do before in delta. And what's really good about the twist is that since phi D1 collapses everything to 1, it doesn't really matter if you collapse or if we twist and collapse, because you're collapsing anyways. And so since these two functions are equal in gamma, they have to induce the same simplicial map from x2 to x1. So in particular, if we now look at the composition, this is saying if you have a composite and you compose, this should be the same as twisting and then composing, which in other words is saying that composition is commutative. All right, so now we have found a way to encode all the desired properties, and we propose that a Picard n category should be a functor from gamma times n copies of delta op to set, such that when you restrict the gamma coordinate back to delta op, what you end up is a Thomson-Money n+1 groupoid with one object. Okay. So how do we connect the homotopy category of these things to the homotopy category of stable n types? Well, the trick is going to be to go through the notion of the gamma objects. So just like a simplicial object in a category is a functor out of delta op, there's a notion of gamma object in a category, which is a functor from gamma to C that maps the set 0 to the point in the category C. Okay, so let's say that we now have a Picard n category, which is a functor like this to set, right? Well, we can curryfy this and we can rewrite this. We know that this is the same as a functor from gamma to the category of functors from gamma up to the n to set. And now, since we're saying that when we restrict the gamma direction here to delta, we need to have a Thompson-Mani n+1 groupoid. What we're saying, in other words, or maybe in particular, is that Picard n categories are gamma objects in Thompson-Mani n groupoids if we take this as the C in this definition that we have right here. So we have a gamma object into the category of functors from delta up n to set, but by this condition, we further know that we're falling inside of the category of Thompson-Mani n groupoids. All right, so Picard n categories are gamma objects in Thompson-Mani n groupoids, but there's more things going on. For example, when we're saying this, we are completely forgetting about the one object condition that we have up here. We're forgetting about what happens in the first gamma coordinate. So it's likely that not all gamma objects in Thompson-Mani n categories are Picard n categories. So which are they? How can we identify these? Well, we can prove that a functor is a Picard Thompson-Mani n category precisely if it is what's called a very special gamma object in Thompson-Mani n groupoids. So this is one of those funny instances where we use like real life words with mathematical meanings. And when I'm saying very special, these words have a precise mathematical definition. There's a notion of special gamma object and a very special gamma object. And they truly are very special. They're really nice. But whatever these are exactly, they are the right notion in the gamma object world that encaptures what it means to be a Picard n category. And the reason why it's useful to characterize them like this is that people in homotopy theory have already taken the job of studying very special gamma objects. So that part was already done for us. And as I'm going to show you now to finish, we can use those to provide a proof that our proposed notion of Picard n categories is the same as stable n types. So let me give you a sketch of how this works. First of all, let's start with the spectra that have homotopy groups vanishing in all negative dimensions. So these are not quite what we want, but it's a good starting place because these were shown by Bousfield and Friedlander to have the same homotopy category as that of very special gamma objects in pointed simplicial sets. So that's a lot of words. We have functors from gamma to pointed simplicial sets. We take the very special ones, and those have an equivalent homotopy category to the spectra having only positive or zero homotopy groups. So this was work by Bousfield and Friedlander in a very classical paper of theirs. And what we do is we show that this equivalence can be specialized to level n. So if instead of all these spectra, we take the n types, the stable n types, and on the other hand, instead of all very special gamma objects, we take the ones whose homotopy groups are in 0n, then the same equivalence by Bousfield-Friedlander is preserved. And not only is it preserved as a functor, it still gives an equivalence between the restricted homotopy categories of these two things. Now, on the other hand side, we have the classical homotopy hypothesis that links Thompson-Mani n groupoids to n types And here I'm taking the liberty of modeling the spaces, which are n types, as the simplicial sets, which are n types. But this is a liberty that I can take because it's a very classical theorem in, let's say, model categories, that these two have the same homotopy theory. So if you allow me to use simplicial sets, we have the classical statement due to Thompson-Money that this is an equivalence of homotopy categories. Now, this one is already specialized to level n. As you can see, we have Thompson-Money n groupoids and n types. But what we do is we show that it can be specialized to taking very special gamma objects on both sides. So we take very special gamma objects on simplicial sets on the right-hand side. And on the left-hand side, we take very special gamma objects on Thompson-Money n groupoids, and we show that you still keep Thompson-Money's equivalence of homotopy categories. And now we're done, because on this side, we have the stable n types like we wanted. And on this side, we can use our characterization that we showed in the previous slide, because very special gamma objects in Thompson-Money n groupoids are precisely what we name Picard n categories. So composing all of these things gives the desired equivalence of homotopy categories. Okay, that's all that I wanted to tell you today. Thank you so much for your time.
Thank you very much, Maru, for the great talk. Are there any questions or comments for Maru? Yeah, I think Paul. Yeah, please go ahead, Paul.
I don't really have a mathematical comment to say other than I just want to say it's a nice talk. I'm a one-dimensional categorist normally. I get vertigo from higher category theory and from homotopy theory, and I was not expecting to understand this talk at all. So I'm very pleased I did get through most of it. Now, Eilenberg, there's a quote from Eilenberg. He said, if you do it properly, you don't need a subscript or something like that. The whole point of introducing category theory in 1940s was to tidy up algebraic topology. And I would say this is an excellent example of that. Thank you very much.
Thank you.
Yeah, thank you very much.
In regards to what Paul was saying, I think that what you're seeing here is that I am also a one category theorist usually. And I did this incursion into higher categories very recently. And I started working myself with two categories and double categories, and those are fine for me because they're very concrete and you still have morphisms and things and you can get your hands dirty. But I was also very scared of higher categories when I was going into this project. So probably what you're seeing here is my process as a one category theorist of going into this world and try to take it as slow as possible.
Right.
So I'm glad that it paid off for someone other than me.
Well, it's good to see a presentation from somebody who thinks in a similar way. But I mean, what frightens me, I think, really about higher categories is that we live in a three-dimensional world, and there are plenty of very complicated things that happen in that three-dimensional. I mean, I'm talking about everyday life world, like knots, for example, which are something you're not going to get in one category theory. You're going to get complications of this kind in by the time you get to three dimensions, and who knows what after that. It can only get worse. So I like the gamma thing. So I normally work with theoretical computer scientists, and that certainly reminds me of the way that those people think. I don't have any more to say than that, obviously.
So could I just make a comment? I'd like to iterate Paul's comment. It was a very nice talk. And I'm a double category theorist, so one degree higher. And I see here that you have all these functors from delta to the n into set. These look more like n-tuple categories than n categories. And so I was wondering, is this a good idea, you know, to replace the n categories by n-tuple categories or not?
Right. So I think what bridges those notions is the Siegel condition, like Paul was highlighting in my slide where I said, okay, we have a multi-simplicial functor, but what makes this n-tuple thing a higher category? And it's the Siegel condition. So perhaps because higher categories are not my forte, that I think that looking at them with a multi-simplicial model that's really combinatorial, for me, it actually makes it easier. Of course, someone who's used to working with, I don't know, theta models or something might think that this has a lot of data that you need to keep track of. But for me, the combinatorics of delta make everything as tractable as possible. And then this Siegel condition that allows you to compose up to weak equivalents is what gives you the homotopy that you need to have a higher category.
Yeah. Okay.
Thank you very much, Paul, for the question. Yeah, Carlos, go ahead.
Thank you, Maru, for this nice talk. I remember when I was in master that I see this problem called, well, in that comment I see the grotesque dream, yeah, and it's really nice to see approved right now that I'm a researcher. My question is maybe I was lost, but could you make precise? So for example, when you have a space and you loop, or if it is possible you make the looping, yeah, how you could see this in the categories, in the groupoids or in the n types, yeah. So I saw that you managed with this that they have some symmetrical monoidal structure, yeah, and also in this direction, yeah. Well, there is this fashion new things of Petri nets. I don't know if maybe you can make a homotopy hypothesis or stable homotopy hypothesis in terms of generators, that you use Petri nets as generators. Well,
they use Petri nets as generators.
Yeah, well, the first question was how you see loops and the loopings, yeah, but in the categorical side.
Ah, I see.
Yeah, so you have a functor that is looping, but when you push all this in the groupoids, yeah, what are you? What is the functor there?
I actually never thought about that. Like you're saying, okay, I think I see what you're saying. You're saying like here we have the infinite loop spaces and we have a delooping functor. Yeah. We have an equivalence that goes to the very special gamma things. What happens if you compose the looping functor with the equivalence? What are you doing in the gamma spaces? I have no idea.
Yeah, for example, the looping is I think it's right now it's clear because you can classify. Yeah, so you are doing some type of classification. Yeah, so you classify your groupoid and you obtain another groupoid.
I mean, there's an obvious problem with looping and de-looping spectra that have homotopy groups between 0 and then are not closed under either. If you loop, the homotopy groups go between -1 and n-1. And if you de-loop, they go between 1 and then +1. So, I mean, the spectra with homotopy groups between 0 and don't have looping or de-looping. Was that, could people hear me?
Weird looks.
Yeah, okay, Omar, es que we don't hear you very well. Well,
Maybe write the answer in the chat. That would be
yeah.
a good idea.
Mm-hmm. Yeah, well, about my another comment with Petri nets, yeah, I was wondering, as you proved the stable homotopy hypothesis with categories, maybe you can choose a set of generators. So, like the graph, for example, you work with a category, you can use a digraph as generators with relations. And if you have a monoidal category, you can use the generators as Petri net. Maybe it could be possible to define a infinity Petri nets as generators, but yes, it's just a suggestion.
That actually sounds really interesting. Yeah, I've never seen, so all that I've heard of Petri nets is in a different context, like modeling chemical reactions or electrical circuits or those kinds of things. I never linked Petri nets with symmetric monoidal categories. But I suppose like in a prop sense, like that would be kind of the connection. Is that where you go to Petri nets from these kinds of structures?
Yeah, I think that we can show that for every Petri net, you can generate a monoidal category, but you have to add some relations for the morphisms. And so to work with symmetrical monoidal categories is the same to work with Petri nets. Yeah. So that's the direction.
That sounds really interesting. Do you mind if I pick your brain about this later?
Yeah. Thank you.
Omar typed his answer in the chat. So maybe, yeah, so looping and de-looping, yeah, sort of might take you into negative types, or, well, I don't know, maybe.
Spectra is not closed under looping or de-looping. Looping takes you to those types. Right, I suppose it might work for the non-specialized version then, where we just have, and like, yeah, like connective spectra and Picard infinity categories or something like that. But still, I don't know how, I've never thought of how the looping thing would work in very special gamma things. At least, so what you do know when you have your functor from gamma to something, if this is very special, what you do know is that x of k is weakly homotopic to k copies of x of 1. So at least that it shouldn't be maybe too hard to study it, in the sense that you really only need to look at what the action is on x1, and that should tell you what's happening in the rest. but as to what's happening on X1, I have no idea.
I think Omar has a question. Maybe if the microphone doesn't work, maybe you can type the question.
Can you hear me now, or do I need to
Yes.
type? You can hear me. All right, great. Very nice talk and very nice work. I really liked the gamma set definition. I was expecting something much more complicated. I was expecting that you would encode the symmetric property by putting it even higher in the categorical direction. So for n types, I think you can just shift up n levels. So an alternative definition should be, you should be able to say that a stable n type is Thompson-Mani 2n groupoid that only has one object, one morphism, two morphism, all the way up to level n. But that sounds, quite a bit more complicated. Have you thought about that and comparing it with your nicer, lower definition?
Yes, yeah, absolutely. So we thought from the start that if any of this worked, then that like stabilization hypothesis should hold as well. So what you're saying should definitely give another model. And at some point we try to make it concrete, and it was true, but it didn't seem illuminating at all, to be fair. And then I believe that we found that another set of authors had pretty much shown that this model, the Thompson-Mani model that we're using, has this stabilization hypothesis. I think it was Rune Housing and I'm blanking on who else. But I'm almost sure that this has been done and it's in fact true. So yes, you could do that extreme shift to have the symmetric structure. But yeah, we were very happy when we were able to characterize these as the very special gamma objects, because that just makes everything so much easier.
Yeah, it's very nice. Yeah. And I wanted to ask one more thing about so like a couple of cases have been proved before, and you could think about comparing the existing functors from Picard 1 groupoids or Picard 2 groupoids to Spectra with yours. That is probably pretty easy for Picard groupoids, but the one that Gursky, Johnson, and Osorno defined for Picard 2 groupoids, that's probably hard to compare. I mean, their model is literally like symmetric monoidal bicategories with all the groupoid properties. Have you, is there like some good nerve for symmetric monoidal bicategories that you could use to compare it with your model? Or
so this comparison is something that we have pending for sure. Like you say, we're able to do the comparison with the n=1 case, which is it's not complete, it's not as trivial as one would expect, but it is pretty direct. Like it holds and it's true. And that's included in our paper. And the comparison with the n=2 model of Gursky, Johnson, and Osorno is way more, like exponentially more complicated. There is a nerve that we tried to use, but then the problem was that we had to work with tri-categories with one object, and that was a bit more than we could handle.
So is that what you do for the n=1 case? You use bicategories with a single object, and then you use something like the Duskin nerve? Or
no. So for the n=1 case, we don't have to go through. So let me try to remember what we did.
So I guess it might be easier to compare with your model if you shift it up to 2 categories, but I don't know. I'm just guessing.
I'm blanking on how we did it, to be honest. We certainly did not use the dusking nerve.
Mhm.
That was more along the lines of what we had to do for the n=2 case. I mean, not the dusking nerve, but like another version of 2-nerve.
Mhm. Oh, right. There's a Pauli lock nerve, I think.
Exactly. Yes. So Pauli, which is one of my co-authors in this project, was, I think, the only one who had a hope of understanding how that nerve could relate to Gursky, Johnson, and Osorno's project, and we were all kind of lagging behind.
Mhm.
But if we ever manage to get together, that would be the next thing to do with this project for sure.
Mhm. And yeah, sorry, let me just ask one last thing and then I'll shut up. But so one nice feature of the Gursky, Johnson, and Osorno model is that they also have like nice explicit formulas for homotopy invariance of the stable 2 type. Like
Wait,
for
sorry,
the K
Amar,
invariant.
you're
And it
breaking up. Would you mind
breaking up.
starting over?
So yeah, Gursky, Johnson, and Osorno, they also have nice explicit formulas for some homotopy invariants of the stable 2 type, like the K invariant, and it comes from like reasonable categorical structure on their side. Do you have nice interpretation of, for example, the K invariants?
No, not yet. That is another thing we would like to do. So they're able to very nicely isolate a bunch of their Postnikov towers, and they get almost all the K. I think not all of them, but almost all of the invariants that you can get out of there. Currently, we don't even have a nice way to interpret those invariants, even for our case n=2. So I would be surprised. I don't want to speak ill of my own project, but I would be surprised if our presentation yielded something more concrete than Gursky, Johnson, Osorno's for the n=2 case. Because their presentation is so fleshed out that I think for computational purposes, it should be richer. But we haven't been able to isolate any of that.
Well, that's a fair trade-off. I mean, your model works very nicely for all n. One would expect that explicit models work better for small n. I think that's reasonable and to be expected. Yeah. All right. Thank you very much.
Yeah, of course.
Thank you very much, Omar. I think there is another question by Daniel Plácido. You might want to unmute yourself, Daniel.
Okay. Hey, Meru. So I was wondering, because these Tasmanian categories are defined inductively, right? So
are defined in what, sorry?
Inductively.
Inductively.
So sorry. So like this approach to the stable homotopy hypothesis, I think it will not work for like infinity categories. For like an infinity stable homotopy hypothesis. Or, I mean, I'm just asking if you thought about it.
Would you mind asking that again?
Yeah, because you're like proving the stable homotopy hypothesis using the tensor-many model, which is defined inductively. So, like in the non-stable case, you have like a very nice way to put like the infinity homotopy hypothesis, right? Between infinity groupoids and topological spaces in general. So I think, would there be like a stable homotopy hypothesis between stable spectra in general and like infinity Picard groupoids, something like that?
Right. So let me share my screen again. So, okay, if we're letting n go to infinity, right, then on the spectra case, you have spectra whose homotopy groups are concentrated in 0 to infinity. So those are what we call connective spectra. It's this thing right here with homotopy groups greater or equal than 0 are the only ones that are not vanishing. And so I suppose in a way, this equivalence by Bausu-Friedlander's already providing a more concrete model for these things in a way. And then I think that in this case, there's a more categorical thing, because here you're still using simplicial sets, right? So it's still kind of topological. I think I want to say symmetric monoidal. What do we need to put here? Symmetric monoidal. So symmetric monoidal categories, I think, are already enough. But don't quote me on that specifically. This has certainly been done. This has been done already, and I'm trying to think of by whom? By Siegel, perhaps?
Okay. Okay, so it's been done. Okay. Thank you, Mary. It was an awesome talk.
Yeah, thank you. I'll send you the if I find the concrete statement that I'm trying to say, I'll send you the reference.
Okay.
I think it was Thomason, not Siegel.
Thomason?
Yeah. It's but yes, it is true that you can model all connective spectra with symmetric monoidal categories. I think that must be. I'm pretty sure it's Thomason. But,
Now I'm thinking Mendel. Wasn't it Mendel?
I think, yeah. So probably one should say Thomason Mendel. I think so.
Okay.
Like the full proof is probably in Mendel. The main ideas are from some old papers of Thomason. Yeah, it's probably more fair to say Mendel.
Yeah, thank you very much, Daniel. Are there any other questions or comments? Well, if not, let's thank Maru for the lovely talk. It was pretty great. Thank you so much.
Yeah, thank you again.